This is a Tesla P4. It is a data center GPU from 2016. It draws 75 watts. It costs about $90 on eBay right now. And it just ran a 27 billion parameter model at 32,000 tokens of context. PrismML says you need a modern GPU for this. Nobody told the P4. This is Wolf Steadman at the local ceiling, where we test the claims everyone else just repeats. Let's get into it. PrismML released Bonsai 27B on July 14th. It is not a new model. It is Qwen 3.627B, Alibaba's dense model from earlier this year, put through quantization-aware training and compressed into two extreme formats. One format is ternary. Every weight is -1, 0 or +1. The other is straight 1-bit, -1 or +1. Both ship under Apache 2.0. On paper, the size numbers are the headline. The 1-bit build is 3.9 gigabytes. Ternary is listed at 5.9. That is a 27 billion parameter model, small enough to sit next to a couple of phone apps, and PrismML is calling it the first 27B class model that runs on a phone. We are not the first to publish on this model. It already has more than 15 YouTube videos and at least 10 blog posts, and every one of them tests it on hardware you would actually buy today: RTX 5090s, an RTX Pro 6000, a DGX Spark, an H100, an iPhone. Nobody has published a number on what is still sitting in home labs and small racks. Pascal and Volta cards from 2016 through 2018. That is the gap we are filling. Before the old hardware, here is what we actually did. We built a 60-probe real-task test harness. Coding, reasoning, tool use, instruction following. We ran it against base Qwen 3.6 at Q4, the ternary build, and the 1-bit build. Then a seed study to check the results were not noise. Then speed sweeps. Around 450 scored generations. Everyone scored by code, not by vibes. The quality story. For ternary, it holds up. Base Q4 scored 50 out of 60. Ternary scored 49, and it is not just us. An independent benchmark run on a Jetson Orin puts ternary at about 91% retention on a harder question ladder. Two independent tests, same answer. Ternary is close to free. The 1-bit build needs a more careful sentence. On our real task suite, it scored 47 out of 60. Still close, but that same Jetson benchmark shows exactly where 1-bit pays. Math drops from 100% to 64. Persian collapses from 80% to 45. Our shorter everyday tasks, including Russian, French, and Spanish, did not hit that wall. So the honest summary is this. Everyday English tasks survive 1-bit, almost untouched. Hard arithmetic and lower resource languages are what you pay for in bits. Interestingly, that is the opposite of PrismML's own benchmark table, which shows math surviving best. When an independent test and the vendor's suite disagree about the failure mode, that is worth knowing before you build on this thing. The bigger surprise was not about quantization at all. It was reasoning loops. We measured non-termination across formats, and the worst offender was the base model at Q6, a higher precision quantization, failing to finish on 23% of our reasoning probes. That is a base model trait, not something the low-bit rebuilds introduced, and we are not alone. An independent review on an RTX Pro 6000 watched the 1-bit build exhaust its token budget before reaching a final answer. It has a one-flag fix. Capping the reasoning budget at 2,048 tokens took Q6 from 19 clean completions out of 26 to all 26. On speed, pre-fill on our V100 was flat across every format, roughly 830 to 920 tokens per second, no matter which build was loaded. Decode is where it splits. Depending on format, anywhere from the mid-20s up to the mid-50s tokens per second. We will come back to why that range exists. Now, the parts that do not show up on PrismML's launch page. First, the ternary build's real size. The headline number is 5.9 gigabytes. That is the ideal information theoretic size for ternary weights. But current GGUF kernels cannot pack ternary values that tightly. They land in 2-bit slots. So what you actually download is closer to 7.2 gigabytes, roughly 22% bigger than the marketed number. Second, PQ20, one of the packed formats PrismML shipped, does not load. Try it, and you get an invalid type error. We hit this ourselves in PrismML's own fork. As of today, if you download that specific file expecting it to just work, it will not. Third, and this one costs you speed. BaseQuen 3.6 has native multi-token prediction heads for speculative decoding. Bonsai's low-bit rebuilds. Strip them out. We counted the tensors, 851 in both Bonsai files, 866 in a head-preserving build of the base. The 15 missing tensors are exactly the speculation head. What is left to claw speed back is PrismML's separate dspark drafter. Their own numbers on an H100 show it delivering a 1.37x speedup. On our V100 running that same drafter, we measured 1.14x on ternary and 1.03x on 1-bit. Call it barely there. That gap is not a bug. The drafter's speedup leans on modern tensor core paths that Volta and Pascal simply do not have. On new hardware, the free speedup is real. On the hardware in this video, it is not. 2 claims have circulated since launch, and we want to be specific about which one we tested and which one we did not. The first is a tool calling drop at 1-bit. That analysis came out the day after release, and it uses PrismML's own benchmark suite. Tool calling falls from 80 down to 66 at 1-bit. A much steeper drop than math. On the vendor's own numbers, that is real, and we are not rederiving it. What we did instead was run our own agentic tasks. A real tool used probes, thermostats, calendars, email triage, multi-step, with a fake tool server checking every call. In our runs, we did not see a collapse that size. Scores held close to base, across formats. 2 things can both be true. The vendor's benchmark shows a steep drop at 1-bit, and our real tasks did not reproduce it. If you are building something tool-heavy, both halves matter. The benchmark says, be careful. Our real tasks say it depends heavily on what you are actually asking the model to do. The second claim is language degradation. Here, the independent evidence is now solid. The Jetson benchmark's Persian ladder collapses from 80% to 45% at 1-bit. Community reports describe the same flavor of problem in Russian. Our own short Russian, French, and Spanish tasks passed on every format. So this looks task depth and language dependent. And ternary holds up far better than 1-bit here too. 67% versus 45% on that Persian ladder. If you work in a language other than English, that is your reason to pick ternary. Now the hardware. This is a Tesla P4. NVIDIA launched it in 2016. Pascal architecture passively cooled. Single slot, 75 watts. Surplus units are selling on eBay right now for roughly $90. PrismML's own documentation lists a practical minimum of an RTX 3060, an Ampere generation card. The P4 is 2 full architecture generations behind that. We loaded the 1-bit build on it anyway, and it has to be the 1-bit here. The ternary's 7.2 gigabytes of weights alone would leave no room for context, and this card's 7.7 gigabytes of VRAM. With the model's 3.9 gigabytes loaded, the KV cache quantized to 8-bit, and context set to 32,000 tokens, it generated at roughly 14 tokens per second. That is a 27 billion parameter model on a $90 card from 2016, at a context length most people only associate with much newer hardware. We want to be straight about what that number is and is not. It is not PrismML's optimized low-bit kernel path. That targets Ampere and newer, where dedicated low-bit instructions exist. What ran on the P4 is llama.cpp's generic CUDA path, the one that works on anything but is tuned for nothing. That is also why decode on our V100 topped out in the mid-50s instead of higher. Same generic path, newer card. There is real headroom between what these numbers show today and what dedicated Pascal and Volta kernels could do. That headroom is the next thing we are looking at, not today's video. So where does that leave you? If you are deciding whether to actually use this, our recommendation is the ternary build. It gives up the least quality against base in our testing, and it puts a 27 billion parameter model within reach of 12 GB cards for the first time. The 1-bit build is smaller, and it is genuinely impressive that it runs at all. But on our numbers, it costs more quality than the size savings are worth for most real work. None of this is final, the way a benchmark table pretends to be. PQ20 could get fixed. What we can tell you is what we measured on our own hardware in the days right after this thing shipped. There is a second piece to this we have not done yet, actually hand-tuning inference kernels for Volta and Pascal instead of running the generic path, closing some of that headroom we just showed you. If that is something you would want to see, tell us in the comments, and if the interest is there, we will bring you real numbers when we have them. If you want the full harness data, the link is in the description. All of it, down to the individual prompts and scores. Subscribe if you want the next one when it is ready. For the local ceiling, I'm Wolf Stedman.